Hello, ladies and gentlemen. I hope you're all doing well. We're going to finish off our 2010-2011 Alberta high school contests by finishing off part 2 of the paper with problem number 5 here. 7 teams gather, and each pair of teams plays one of 3 sports, so that no set of 3 teams all play the same sport among themselves. Immediately I'm starting to think Steiner triples systems, which has come up on some contests over the last few years. Anyway, that's just an initial thought, just because I see the numbers 7, 3, and 2 when it comes to pairs. So these are numbers I think of when I think Steiner triples. Anyway, a triplet of teams is said to be diverse if all 3 sports are played amongst themselves. So you've got a team A, B, and C, and so A plays B and they play water polo, and A plays C and they play, I don't know, rugby, and then B plays C and they play lacrosse. And that's sort of the idea here. We can visualize teams playing against each other by drawing lines between them. So a triplet team is diverse if all 3 sports are played amongst themselves. Otherwise, you can get something like Team A, Team B, Team C, and then maybe they all play water polo amongst themselves, or maybe 2 of the teams play, or 2 of the pairings play lacrosse, and then the other pairing plays rugby. And you can get those sorts of things, but they're talking specifically about these multicolored sort of triangles, that's just a visual representation of them, but that's called diverse. Okay. So, no set of 3 teams all play the same sport amongst themselves, so I guess this would be impossible because all 3 of those teams were playing water polo. Okay, what is the maximum possible number of diverse triplets among the 7 teams? Okay, so I don't think this is Steiner triplets. Steiner triplets are just ways of saying, okay, I've got, 7 things. I did a question a little while ago. It was people riding a bus, and you had 3 people in this. It's ways to. Steiner triples are ways to make groups of 3, so that each pair of people only are in one group, but all pairs are in some group. So here's A, B. A and B would never be together again, and you can keep going. Okay, but I don't think that's quite what this is, because, and I've been drawing this already, we sort of have the games that are played is kind of important. Now, we know there's 7 teams, so one thing we could do is we could put all our teams together, and this is fairly common when I'm trying to talk about tournaments and questions. I tend to try to visualize things by drawing connections. So, A plays B, A plays C, A plays D, but here I'm going to be coloring things to indicate, which sport is being played. Okay. And so the diverse ones, as I've already sort of drawn, are going to be when you get a triangle that has all 3 color sides in there. But what we also need to remember to avoid is you can't have a triangle that's sort of monochromatic. It's all the same color. So there's going to be 2 parts to this question at least, and I don't know how long each part should be, but for a general question like this, they want to know the maximum number possible. So we're probably going to develop a little bit of theory to maybe create an upper bound, say that, at most we could have 6 diverse triplets. I don't know if that's the answer. But then, if we show that you can't have more than 6, we actually have to come up with sort of a visualization or an expression of these 2 teams play this, these 2 teams play this, that does, in fact, achieve our upper bound of 6. Okay, so there's going to be those 2 parts. And one thing we can do as we start out with this is we could maybe play around and see what we can see. I know this can't be green here, so maybe make it red. Maybe make this one red. Can't have a red up there, but we could try a blue. And we can also try and maximize our number of distinct triples, or diverse teams. Okay, so you can, maybe I've got a red going from A to B, a blue going from A to E, so maybe connect that up with a green. Okay. Maybe do a blue from G to B, but you'll notice I'm slowly losing track. This is getting more cluttered, so it might be harder to tell. So there I just drew one in because I had A to G was green, A to C was red, and now G to C is blue, but you'll notice B, C, G just became a blue triangle, so I can't do that. Okay. I suppose it could be a red triangle. So far, no harm in that. Put a green one here. That gets me a nice little triple with A, C, and D. What else? Oh, we could have a nice little triple here. That doesn't break any rules so far. Okay. And what we're starting to get is this, what's called a complete graph on 7 vertices. Okay, you've got 7 points, and all the points are connected to every other point. Maybe try this here. And I'm just trying to go slow and make sure I don't get any triangles that have all 3, because you can't have all 3 games being played. Now, B to F can't be green, because B to E and E to F are green. It looks like we could have it be blue. I don't see any reason why not to. I would have liked it to be green because I've got a blue here and a red from G to F. But c'est la vie. Now that does give me A, B, F is diverse. And I'm just sort of playing around. What else? A has 6 vertices, or 6 lines coming from it. G has 6 lines coming from it. B doesn't have 6 lines. C doesn't. D doesn't. E has 6 lines coming from it. We need one more to F. F to C. It can't be green because of C, E, and F. It can't be red because of F, G, and C. Could it be blue? I hope it can. Oh, it can't be blue because of B, F, and C. So these might be a little harder to make than I thought. I'll make it blue and then make this green. No, it can't be green. Oh, goodness. I wonder if this is... Alright, so far that looks good. But I wonder if it's even possible to have such a configuration of teams. Maybe the answer is 0, because there's no way to actually make the teams work like this. I don't know. BD can't be blue, even though I'd like it for the BCD triangle to be diverse. How about red? There's not a lot of red going into B. So that seems good. And then we just need D to F. It can't be red because of GFD. Can it be blue? Yeah, it looks like it could be blue. Okay, so there's, I guess, an example of something that's completed. We could painstakingly try and find the diverse triangles. Maybe we should have kept track of them as we went. But at least that appears to be an example that would work. Maybe I didn't make it so nicely geometrically or anything like that. But this is the sort of thing that could represent our teams in the various sports that they play when they're paired up. Okay, now, for a complete graph like this, there's some things that we might know. So, for example, between any 2 points, we get a line. So if I choose 2 out of my 7 points, I get a line. So using some choose notation, if you're familiar with that, or 7 times 6 over 2 times 1, you'll see that there are 21 lines. So there's 21 pairings of these teams. Another way to say it would be A has 6 games to play. G has 5 games that aren't with A to play. F has 4 games that aren't with A or G, so 6 plus 5 plus 4 plus 3 plus 2 plus 1 is 21. That's another way to see it. Okay. How many, what are the triplets? Triples or triplets? A triplet of teams. Well, there's going to be any 7 teams, choose 3 of them, that'll form a triangle. And that cancels out with that, so 35 triplets. Okay. Now each line appears in triplets. How many times does each line appear in a triplet? Well, there's 3 lines per triplet times 35 triplets. So that gives me 105 lines. Now, I only have 21 lines, so if I divide by 21 lines, I can see each line is in 5 triplets. Okay? So that's an interesting observation. Each line is used 5 times. So that might be something worth noting. Okay? And each triplet uses 3 lines. So there's 35 triplets. Now, that's definitely an upper bound. We can't get any more diverse triplets than 35. But I'm going to suspect that 35 isn't actually possible. You'd need to have everything be diverse. And I just don't think that's the case. Here's why. Think about A. Right? Going to B, C, Team A playing Team B, playing Team D, playing Team G, those sorts of things. So pick a color for AG. Now, if I pick the same sport for A and F to play, I automatically know no matter what color I pick, no matter what sport F and G play, I know for a fact that I don't have a distinct triplet. I don't have all 3 colors because I've got 2 blues already. So, okay, I don't pick blue. Maybe I pick red. And then you could definitely get a green here between F and G, right? Now, what about what sport should AE play? Well, if it's a blue, again, AEG can't be a distinct triple. If it's red, same reasoning, AEF can't be. So we're going to have a green. And then, hooray, you can put a blue here, and you've got another triple, and you can put a red here, and then, oh, look at that, we got a nice little family of triples here. But what do A and D play? What sport do they play? Do they play red? Which I think I said was rugby off the top of my head. Well, no, because then A, D, and F don't work. Okay, could they play green? Well, no, then A, D, and E. How about blue? No, and then A, D, and G would cause a problem. Okay? So we get this sort of issue that you're definitely limited by the number of diverse triples. There's definitely sort of, by looking at each vertex, you can see what's going to go down. So if I see 2 of the same color vertex, that definitely means I have at least 1 triangle that is not monochromatic, because we can never get all 3 blue. So whatever this is some other color. But I can definitely see, okay, there's 1 less diverse triple that I'm going to have. Right? If I see 3 of the same color, then if we just clear up a little bit of this clutter here. So if I see 3 of the same color, then that's 1, 2, 3 triangles that wouldn't work. If I see 4 of the same color, that's 3 triangles, 4, 5, 6 triangles we lose. Okay, so the number of same color that I get, so if I see 4 blue, I should have 4 choose 2. That's how many distinct triples I lose. Okay. So we probably want to write that up. So notice And you might also wonder, okay, are we double counting? If you were allowed to have, if they changed the problem and you were allowed to have sort of all blue triangles, then when you go to A, you would say, all right, I'm going to lose 6 here. But then when you go to C, you'd say, oh, I'm going to lose at least 1 for this triangle. But you're counting this triangle multiple times. Well, they've eliminated that. There's no way to get all blues. So, if you see A has these 2 blues, CG can't be blue. So when you go to G, you won't say, these are the same color, you lose a triangle. No, you will ignore it. So what we need to do is just sort of go around to each vertex and count what we lose by the multiple colors that we get. So notice that what's the best way to say this? So a non-diverse, non-diverse is fine. I can't think of a better term. So a non-diverse triplet can be recognized by a vertex having, let's say, two colored lines, 2 lines meeting at it of the same color. Okay, so that's something worth noting. Let's also note that a non-diverse triplet has only one such vertex. Okay, as we cannot have all teams in the triplet play the same game. So the other vertices will be this blue and then some other color. Blue and then some other color. So that's an important fact. Okay. So the number of non-diverse triplets having their repeated color meet at vertex A, for example, is the sum of B choose 2, G choose 2, and R choose 2. I'm going to explain these in a moment, where 1 choose 2 and 0 choose 2 are equal to 0. And B, G, R are the number of lines at A that are blue, green, and red, respectively. Okay. So, to count non-diverse triplets, just count the number of non-diverse triplets at each vertex. Okay? So, for example, and this would actually make this this example that we started with, it's now I don't actually have to go hunting for the diverse triplets. What I can do is I can say, okay, A. At A, I see 3 blue. 3 choose 2. I see 2 green. And I see 1 red. So 3 choose 2 is 3, 1, 0. So we lose 4 triplets. There are 4 triplets out of my 35 that can't be distinct. Not distinct, diverse. Okay. At G, what do we see? We see 2 blue, 1 green, 3 reds, so we lose another 4 of my 35 triplets here, but they're going to be different triangles that are not counted by the ones from A. At F, I see 3 blue, 2 green, and 1 red. So it looks like we lose 4 again. Am I always guaranteed to lose 4? I lose 4 at B. I lose 4 at C, although maybe that just happens to be the way this one was made. It looks like we're going to lose 28 of them, and so maybe 7 is the most we could ever have. At D, I see 2 blue, 1 green, and 3 red, and so I lose another 4. And at E, I lose, so I see 2 blue, 3 green, and 1 red, so I lose another 4. So this one has to have 7 diverse triples. Now, let's see if we can actually find those, just to make sure we absolutely understand and that our theory is correct and that there are 7 of them. So let's just take a little bit of time to try and find them. So I notice A, C, F. That's 1. Use a different color now. Well, this is hard to find them. A, C, E. That's another one. Maybe I should write them down. So A, C, F, A, C, E. Anything else coming from A? So an A with a blue and a red, the only thing left would be A, B, C, and that's not. How about A and a blue and or red and a green? A, B, A, C, F, yeah, we did that one. A, C, G, no, that's not going to work. Oh, A, C, D. That's another one over here because of the green. Okay. ABF, no. ADF, no. AEF, no. AEG, no. ADG. There's one for us. And ABG is also a no. So I think that's it for things involving A. So I'd like to, if I could, just sort of ignore these ones. Let's move on to B. Things involving B that don't involve A. BFG, no. BEF, BGF. BDF, BED, no. BCF, BCG, no. BCD, no. BCE, no. Doesn't look like there's going to be any for B, other than the one we already... Actually, we don't have any for B. That is quite peculiar, but okay. That's perfectly fine. That's allowed. How about C? Anything with C? So, CGE. You can see that one right away. CGD isn't going to work. CFG isn't going to work, so that's it for C and G. C, F, E, no. C, D, E, no. And C, F, D, no. So I think that's it for C. So we've got 5 of them so far. D, E, F, that's definitely one. D, G, F, no. D, E, G, no. And then E, F, G, yeah. Looks like we got 7, so our theory worked. Although if we were confident in it, we didn't have to stop and do this. But that's kind of nice. So 7. But you notice I didn't have to go hunting for them. I could have trusted the math. The question is it just a coincidence that we always have 4, or is there some reason? Is there some reason we have 4 here? So what sort of colors can meet a vertex? And I'd like to minimize this if possible. And, you know, if I find a way for me to only lose 3 triangles at A, that doesn't mean, okay, you can lose 3 everywhere. And there's definitely a complete graph that we can draw that works that way. Remember, there's 2 parts to this. Getting that upper bound and then showing it can happen. Okay. But, all right, let's imagine A. What could we have? Well, we could have something silly like all the same color. But you're going to lose 6, choose 2. Which is 6 times 5 over 2, so that's 15. We definitely don't want to do it. Actually, 4 is the one to beat. I know I can do 4. And that's with 3, 2, and 1. What if we did something like 2, 2, and 2? Because then you got 2 blues, 2 greens, 2 reds. That would mean I lose 3. Okay. So that happens. Now, what else could we have? So 2 of each loses 3. Well, we've already seen that if you have 3 blues, you'll have 3, choose 2, and that's 3 plus whatever else. So 3 of any other color, of any color, means at least 3. In fact, if we have 3 reds, then we'd lose 6 triangles, and if we drop that down, we know this is 4. Okay, so the best we can do with 3 of a color is lose 4. Okay. So I think the best we can do is lose 3 on each vertex, and that's if it's possible to do this. So that would mean we need 2 blues for each vertex, 2 reds for each vertex, and 2 greens. But if that were the case, then with 7 vertices, we'd lose 21. The best we could do is have 14. Okay? So, just a quick note, if we don't have 2 of each, by pigeonhole principle, we will have at least 3 of another, or 3 of one color. Okay, so the best we can do is 3 non-diverse, I think I called them triplets. Per vertex. So overall, 21 non-diverse. And therefore, since there's 35 triangles overall, that would be 14 diverse at most. Okay? Now, there might be something else. There might be more math we haven't thought of. That means we can't actually get that 14. Maybe, it has to be 12 specifically or something like that. But let's see if we can do this. Can we actually do, 2 blue, 2 red, 2 green everywhere? Right? If we can, then we're done. If we can't, we need to sort of come up with a reason why not and get a better bound than 14. Okay, well, let's try it. So 2 blues here, 2 reds here, and 2 greens here. Now, we're not going to focus on trying to make diverse triples. As long as I can do this green-blue stuff, we'll be fine. As long as I can manage to get them, we're okay. But we've got to watch out for those monochromatic triangles. Those all blue, all green. So let's put a green up here. And maybe we'll put... The only thing I need to worry about is that green couldn't go to GF. Couldn't go GF. That's about it right now. Everything else is perfectly acceptable because I'm sort of basing it off of AG. Okay, so we can do that and that. So everything's good now. Now let's go to F. Okay, so I've already got a green and a red. We can try and finish those off. Can I put a red with EF? No, I can't. But I could probably put a green there. So there's my greens done. Let's put a red to D. And now let's try and put blues everywhere else. Blue here works fine because AF is green. And a blue here is fine. Again, AF is green and FG is red. So I'm not seeing any monochromatic triangles here. But I think this is going to get harder to put together. We might actually need to start looking for patterns rather than just trying to come up with this off the top of our head. Let's go to B. B has 2 blues already. It needs another green, and then it needs some reds. Okay. Now, it can't go to E. E already has 2 reds, but we could get another red to D, I think. DF is red, but BF is blue. BG is green, and AB is blue, so those are fine. And we could put one over here to C, and then make BE green. So that's not going to cause a problem with BF, or BG, or BA. So it looks like we're happy. We've just got 2 more. Oh, no. Couldn't put a red one to D. Okay, this is trickier than I thought. Because D and E can't get another red. So, we've got to come up with a better way to do this. I mean, maybe I just need to go back a couple steps, but I feel like there's got to be a nicer way to do this, or maybe it can't be done. Okay. What if we just try and place the blues for a moment? Maybe make AB blue. Oh, you know what we could do with some nice symmetry? So A went to its neighbor, so we'll make B go to its neighbor. And if you look at that, we've got a nice little heptagon, but A has 2 blues in and out. G and F have 2 blues in and out. Could we do the same thing with our reds? So we skip over the next one. And yeah, because it's 7, so this technique would work. So what I like about this question is we could easily scale things up a bit. There we get back to A. So anything that's relatively prime, any prime number would work. And then you would want the number of colors to be that prime minus 1 over 2. Yeah, and then you would you could always get. So if we had P teams and P minus 1 over 2 colors, where P is an odd prime, you would lose P minus at least P minus 2 non-diverse teams per vertex, and so you'd have P vertices. So that's the largest number of non-diverse that you would get. And it's P times P minus 1 times P minus 2 all over 6 total teams. So you'd have P times P minus 1 times P minus 5 all over 6 is the most diverse teams you could get in such a situation. 7 times 6 times 2 all over 6, that's 14. That's kind of cool. Anyways, let's actually finish this up. But the sort of irregular or star heptagons that we're making will always complete. Go to C, go to F, because we're just sort of going over by a certain amount, but 7 is relatively prime to the 3 we're skipping, or the 2 that we're skipping. So F goes to B, B goes to E, and then E goes back to A, and that'll work. So this, and you could explain the geometry or the symmetry that's going on here, but you could just leave it at the end and say, this clearly satisfies the 2-color per vertex condition. So 14 diverse triplets is the most you can get. So we know that's the most, and we actually were able to exhibit it. So answer here is 14, and we're done our proof after a nice little explanation. Okay. You probably could have approached this without the geometry, but really anytime I've got tournaments, I've got teams playing against each other, I tend to draw these pictures, these diagrams, and they're very, very useful. I can't even imagine this question without it. I'm sure you could do it, but it would be much drier to try and work through. I like the pictures, I like the colors. It's a good question to end the paper on. And we have, in fact, finished, so that's it for our 2011 Part 2 paper. If you're looking for more Part 2s or more Albertan contests, by all means, browse around the channel. But that's it for me. Hopefully you've enjoyed the paper. If you have, feel free to throw a like on the video or leave a comment down below with feedback. But that's it for me. Have yourself a wonderful day.